Welcome everyone to this year's XConf and my keynote, Why Does Yesterday's Best Practice Become Tomorrow's Antipattern? We hear the term best practice all the time in the software world, so much so in fact that it has become a sort of a negative trope unto itself. In fact, most people when they say best practice, they put air quotes around it. But in its best light, it's a method or a technique that has consistently shown results superior to those achieved with other means and used as a benchmark. But what happens in our industry all the time is we develop these best practices, something that consistently has shown good results superior to those achieved by other means. But then it gradually becomes a bad thing rather than a good thing. And it becomes gradually an anti-pattern, which is the second part of my title. Now, a lot of people use the word anti-pattern just as a synonym for the word bad, but we don't need that because we already have a word for bad. It's the word bad. An anti-pattern is specifically something that seems like a good idea, but then eventually leads you into a bad place. On Martin Fowler's site, which is the great definer of things in software, he has it as an anti-pattern as a solution that initially looks like an attractive road lined with flowers, but further leads you into a maze filled with monsters, which is a great description of an anti-pattern. So why does this keep happening to us in the software world? Because it seems like it happens all the time to us in the software world. Well, it happens not just in the software world, it happens everywhere. And in fact, if you want a great example of that, just look down. This is being done remotely this year, which means that most of you are watching this in front of a computer. So look down at your keyboard for just a second. And of course, you realize that this keyboard layout is not the most efficient possible keyboard layout for various reasons, which I'm going to get into. It exists in this way, the QWERTY keyboard, mainly because of this. The manual typewriter, which is the first version of a typewriter that we had. And if you're unfamiliar with one of these, the way that this worked was that it had these arms that would fling up and hit a ribbon against a piece of paper to type a letter on that piece of paper. And the problem was that really fast typists on a mechanical typewriter, if you've typed too fast, both arms would come up together and hit the page at the same time. And that would cause a bad letter to show up. And so we had other arcane technologies like whiteout, which was artificial paper that you could paint over that and then carefully type back over it again with these manual arms. And so the QWERTY keyboard layout was created so that fast typists had to alternate hands as much as possible, which reduced the risk of the big hammers hitting the page at the same time. And of course, the history of all this is laid out, like many things, on Wikipedia, the QWERTY keyboard and where this came from. But, you know, nothing in the modern world is ever completely black and white or completely obvious. And in fact, you can find things that now talk about the lies you've been told about the QWERTY keyboard, that it wasn't just the alternating hands, although that was part of it. But it turns out that during that time, manual typewriters were also heavily used by telegraph operators. And they would use one hand for the telegraph and one hand for the typewriter to type out the contents of the message. And so it was also optimized for telegraph operators to be able to move and type with one hand instead of two hands. And so there's a fascinating history behind how we ended up with the keyboard shape that is in front of you. And of course, we know that the Dvorak keyboard is much more efficient, but once you've learned to type one way, it's really difficult to reteach yourself how to do something as fundamental as typing. And even if it's more efficient, you're often reluctant to try to do that. Now, I did used to work with a developer who really, really loved the Dvorak keyboard layout, and he also loved the VI editor. And so everybody else in the project was using regular QWERTY keyboards and TextMate because it was a Ruby on Rails project. But we accommodated that developer on all the pairing stations by setting up a hotkey that would swap between Dvorak and QWERTY, which is great unless you were a QWERTY user that accidentally hit the hotkey and then couldn't figure out how to get it back. But that just proves dedication, because VI is actually optimized for the QWERTY keyboard. It's more difficult to use with Dvorak, so you have to be really dedicated to be obstinate to want to do VI and Dvorak. But of course, a lot of people are that way. But there are other interesting side effects of this design decision for manual typewriters that have bled all the way onto computers and then smartphones and tablets for the QWERTY keyboard. And one of those really unexpected side effects of this is documented in this fascinating blog entry called the missing 11th of the month. It turns out this researcher has done some research, because clearly he or she has too much free time in their hands, and scanned all of these historical documents to look at the distribution of important dates, important events on days of the month. And it turns out when you do that, the 11th of the month is notably missing from history. Now, there's certainly some things that happen and get documented on the 11th. September 11th was a great tragedy in the US, so there's a lot of things about September 11th. But if you look at the distribution of all dates, the 11th is almost non-existent. And he wondered, why is the 11th so elusive? And it turns out it's because of this. Because you'll notice this typewriter has no one key. Because it turns out the glyph for the 1 and lowercase l are the same thing. And so it was a best practice to leave off the extra 1 key and just use the lowercase l anytime you needed a 1. The problem, though, is when you feed that to a 20th century optical character recognition scanner, it reads this nonsense word LLTH, not 11th. And therefore, the 11th disappears from history if you have to scan all those documents. So it happens to all of us, not just in the technology world. But let's look at some technology examples of yesterday's best practice becoming tomorrow's anti-pattern. And probably the first and most famous, one of the most famous one of these is the famous Dijkstra paper about use of goto considered harmful. This was a paper that he created in a talk that he delivered that almost caused a riot in the software world by suggesting that the prevalent way of doing software at that time, using gotos, might not be the best way to write software. And of course, this ushered in the structured programming revolution. But you see this constantly in tech stacks. So here is a history of the database access technology in the .NET stack. And it changed every year for a different acronym. They used every combination of the letters A, D, and O except DOA, which is the acronym for dead on arrival in the US. So that's probably why they didn't use that one. But they've used all of them. And then you keep going forward into history. And then the last stuff you look at is talking about cloud and moving all this stuff to the cloud. Maybe no thing exemplifies this, what we used to think was the best practice is now an anti-pattern, than enterprise Java beans. This was touted as a great solution to a lot of complex problems for a while, but then we realized that no, this is the complex problem we need to solve, is the enterprise Java beans, not the problem it supposedly is solving, which is just making a lot more accidentally complex. And of course, we don't want that. Lots more examples of this from the technology world around the way we use things like tools. For a long time in the software world, it was considered a best practice for projects to have an integration phase at the very end of the project, where developers were expected to work in isolation from each other for days or weeks at a time. And then at the very end of the project, they were expected to integrate all that stuff together to create a release of that software. And not surprisingly, that was a pretty painful process on a lot of projects. And in fact, there's a pretty strong correlation between how painful that was and the size of the project that you're on. But then, of course, in the early 1990s, Kent Beck and the other developers of the XP framework came along and rethought a lot of those best practices in the software world based on their experience. one of the things they had direct experience with was, we've noticed on projects that if we are more aggressive about integration, it seems like we spend less time overall doing integration. So we should invent continuous integration, which is basically what they did. That every time you make a substantive change, you check it in and you constantly do that all the time. But this is an interesting example because it has informed a couple of other revolutions in our tech world, one of which I'll talk about a little bit later in this keynote. But this idea of automating things to get rid of accidental complexity, because it turns out that when you do continuous integration, you spend less overall time managing merges than you do if you do a big bang integration phase. Because if you let the complexity build up and build up and build up and then try to untangle it all, it takes forever. If you tackle the tangles as they happen, you end up spending less time untangling the big giant thing. And so you spend less overall time with merge headaches and continuous integration than you do in continuous integration. So it's not a one-to-one trade-off. There's actually more efficiency to be found by doing it more often and more aggressively. So let's talk about more reasons that this keeps happening to us. And one of the reasons is definitely increased tech stack complexity. Well, that's hard to say. So if you go back to, for example, 2005 and look at the typical tech stack, it was a browser, some sort of server, a database, and maybe reporting. And you could change the labels on the boxes, but it was pretty much that. Fast forward now to the modern era, and there are a lot more moving parts in our tech stacks. We have cloud, we have intelligence and analytics, and all these different options for platforms and architectures and technology stacks. And one of the problems you have when you build a more complex technology stack like this is something that I refer to as primordial abstraction ooze. That's the technical term for it. Because when we build up these technology stacks, we're building layers of abstractions, because each of these is not a perfect mapping to the one below often, but a pretty good, 98% of the time that mapping works correctly. And then we just forget that it's an abstraction until it breaks somehow. And then suddenly the fact that it's an abstraction comes back to us in a really bad way. And the way this manifests here is that you get some sort of exception way down in the bottom of the stack. And then by the time it manifests up into a user interface, it has created a truly impressive stack trace of some kind that takes a lot of untangling to figure out what that root cause was. This is what I refer to as abstraction distraction. The more abstractions we build, the more shaky the tower gets, because sometimes those abstractions break and they cause a cascading breakage. And so the more complex our moving parts get, the harder it is for us to maintain good stability in our systems. And of course, that drives a lot of breakages. But another big reason for this is misunderstanding the real trade-offs that exist in the software development world. I spend a lot of time in the software architecture space, and everything in software architecture is a trade-off. In fact, in my book, The Fundamentals of Software Architecture, my co-author, Mark Richards, and I codified the first law of software architecture, that everything in software architecture is a trade-off. But then you run into things in the real world like code reuse. And a lot of organizations still believe that code reuse is purely a force for good with no negative trade-offs. But what I want to call out as one of the drivers for best practices becoming anti-patterns is what I call code reuse abuse. We've been taught this idea that code reuse and components and software are sort of like plugging Lego blocks together. But there's a great quote by John D. Cook, who's a famous mathematician and a writer in the software world, that says that software reuse is more like an organ transplant than it is snapping together Lego blocks. And I definitely agree with that, having seen that happen a few times. And we see this all the time in the software world. In fact, there was a great example of this just a couple of years ago when 11 lines of code broke the entire internet for a couple of days. You probably remember the leftpad.io happenstance that happened a couple of years ago where a developer decided that he didn't like something about the naming policy of packages in that world, and so removed this code that a whole bunch of dependencies relied on in that world, and it broke Node and a bunch of these famous platforms for a few days until they actually broke their own policy and reinstated that code without his permission. You can say bad things about Maven, but Maven never actually broke the internet for several days. But this is actually something that is worth pointing out here, a common problem that we are facing right now that's leading to a lot of complexity, and it's transitive dependency management. This is not an unusual transitive dependency graph for a JavaScript project now, and this is insanity, because as each one of those things change, it might break something, and that creates really brittle software when you get that much incremental reuse at that level. And so this is something we're actually going to have to resolve as an industry. And in fact, our colleague, Chris Ford, who's no relation to me because he's in another country, has a great expression about this, that transitive dependency management will be our go-to considered harmful moment. Just like the Dijkstra paper was a huge wake-up call for that ecosystem that, hey, this is a big problem that we need an innovative solution for. I think we've almost reached that point with transitive dependency management in the software world. So I want to pause for just a moment and get a little bit philosophical and talk for just a bit about the underscore character. Why is that there on your keyboard in front of you? Because every display from a computer, all the way back to these mainframe terminals, all the way up to your modern phone and tablet, every one of them only allow you to type one character in a character slot. And so what is the underscore really there for? Because you can only type an underscore into that character slot and then you're done. You can't type any more in that slot. Now, developers think that it's there so that we can create variable names by tying things together with the underscore, like a foobar, etc. But why is it really there? What is the real purpose for this thing? Here's my foobar example. That's not why it's there, even though we've co-opted it to use it for that. The reason it's there, this is what I refer to as the Zen key on your keyboard that's in front of you right now, because it can only underline nothingness. You can't put anything else in a space where you've underscored something. So you're just always underscoring a blank space when you use this key. Why is this key even on your keyboard? I'll tell you exactly why this key is on your keyboard. Because of this. Because on a manual typewriter, you didn't hit a hotkey on your keyboard to turn on underline. What you did was type it and then move the carriage back and then use the underscore key to underline it. That's why we have the underscore key that we've co-opted for variables on our keyboards. Even now on your iPhone and your iPad, it has a QWERTY keyboard that has an underscore key on it. A great example of yesterday's best practice becoming tomorrow's antipattern, which of course tomorrow in that case is today. So the other reason for this, of course, is the fundamental nature of the software development ecosystem, which we characterized in our evolutionary architecture book as what we call a dynamic equilibrium. So if you think about all of the tools and platforms and approaches and practices and all the things that we know about software up until 10 minutes ago, that is the software development ecosystem. And all the pieces fit together and they make sense together, but it's extremely dynamic and may change and shift at any time without warning you. And a great example of that is when Docker hit our ecosystem a few years ago. Once Docker hit our ecosystem, it changed our ecosystem forever. Even if you're not using Docker yet, the presence of it in the ecosystem fundamentally changes the kinds of decisions you can make and the future decisions you may make within that ecosystem. Nothing in the software world ever stays put or is static. And here's a great thought experiment for you. Take a computer of some kind, like a laptop, install a bunch of software on it, and then put it in a closet for a year. After that year is over, take it out of the closet, plug it back into the internet, and what's the first thing it's going to want to do? 57 updates available, because even though you didn't change a single byte on that computer, everything in the software development ecosystem continued to move and change. There's a great quote from the inadvertent poet, Donald Rumsfeld, who used to be defense secretary in the US, that talks about there are known unknowns. That is to say, there are things we now know we don't know, but there are also unknown unknowns. There are things we do not know we don't know. And this is the fundamental problem in the software development world, are the unknown unknowns, the fundamental changes that are happening in our ecosystems all the time that we cannot predict. And so how do you solve that problem? Well, this may be belated, but perhaps the title of this talk, rather than why does it become tomorrow's anti-pattern, maybe the title of this talk should have been how to avoid yesterday's best practice becoming tomorrow's anti-pattern. So one of the things that we have learned about software architecture is you definitely want to try to avoid the big ball of mud pattern. And we've also shifted our perspective to domain-centric architectures. And what does that mean? So if you look at the traditional layered architecture, which we've also moved away from, with a presentation layer and business rules, persistence, et cetera, where do concepts like catalog checkout live in the layered architecture? Well, parts in the presentation layer, parts in the business layer, parts in persistence, parts in the database. And so we've taken that domain concept and smeared it out across these technical layers. And we built a lot of architectures around different kinds of technical partitioning, but every one of those forced us to break apart our domain workflows and impose this other layering on top of it. This is, of course, why you see domain-centric architectures like microservices, like modular monoliths becoming much more popular now, because every workflow, every domain has a certain amount of semantic coupling. The details of how that workflow works. And if you have to break that workflow up into some sort of technical partitioning, it becomes more complex. So the way you keep software the simplest is to maintain as close as possible fidelity to the inherent complexity of the problem rather than splitting it across somewhere else. And of course, we figured out that there are lots of benefits to domain-centric architectures around team structure and the inverse Conway maneuver, around things like governance and automated governance, around controlling what are the unit of changes within your architecture, and coupling. Coupling is much lower in these architectures because you isolate it down to a bounded context. So all of these are benefits of that idea of domain-centric architectures. The other thing that we have to do in our world is realize that everything is going to keep changing forever in our world. We're never going to make it stop changing. It's just not the nature of our ecosystem, which is, of course, what we talked about in the evolutionary architecture book. But this sort of begs the question, why are organizations trying to predict the future? Well, obviously, if you can predict the future, we can plan better for it, and it's less expensive to adapt to it if we can predict correctly. But what if you assume that software is going to continue, the software development ecosystem is going to continue to change at least the rate it's changing now? Think about 5 years ago, what software architecture ecosystem looks like before cloud and Kubernetes, and now try to picture what 5 years in the future is going to look like. There's no way. It changes too fast and at too unpredictable a manner. And so evolvability is your best hope. Build adaptability into your systems as you go. And that way you can adapt to those changes as they occur in our ecosystem, which is another way of saying embrace experimentation on software projects. This is one of the things that evolutionary architecture enables you to do, and get away from this idea of coming up with clever ideas and implementing them without being able to vet them with your users. So create an experiment, quantify that thing, get outcomes, and then feed that back into your decision process. And what that allows you to do ultimately is get to hypothesis and data-driven development, modeling the things that you're building based on what your actual customers want and need versus what you're trying to predict they're going to need at some point in the future. And so let me give you a case study to wrap all this stuff up. And it's a great example from the evolutionary architecture world of the way things work in the new world, and a way of getting away from some of the fear and uncertainty that some people have about this world. A lot of developers think that when you move to really aggressive agile engineering practices like evolutionary architecture, like continuous deployment, then you automatically take on more risk. But it turns out that it forces you to think about ways to mitigate that risk. And this is a great example of that. This is from the GitHub engineering blog in an entry they called Move Fast and Fix Things. GitHub is a very aggressive, agile engineering organization. They average 60 deploys a day. And they also operate at such scale that one of the engineers here said that they see every boundary condition almost instantaneously because they operate at such high scale. And this article is about one of the problems of that scale, which is the way they merge things. Turns out since day one at GitHub, the way they've merged two files is to shell out to a shell script, tell command line Git to merge it, and then suck it back into GitHub. And that works great because command line Git knows exactly how to merge things. The problem is it doesn't scale particularly well. So that's the problem they were forced to attack. And so they went and rewrote merge into their own in-memory version. And they did due diligence testing against the merge spec from Git. But now here comes the scariest part of my whole keynote. Now they have to put it live. So what they did, and open source so you can take advantage of it, is to create this tool called Scientist. What Scientist does, and they wrote it originally in Ruby and imported it to about a dozen or more other languages. What Scientist allows you to do is conduct experiments at the architecture level. Each experiment has two blocks, use and try. Use is the old code that we're in the process of replacing. Oops, sorry, went too far there. Use is the old code that we're in the process of replacing, and try is the brand new code we are trying out. So when it hits one of these experiment blocks, it always executes use, and that's what it always returns to the user. But you can also configure it as to how often it also executes try. So for the merge experiment, for 1% of the cases, they also did try. And in that case, it randomized the order in which they're run, measures the duration of everything, compares the result of try to use to make sure they're the same, swallows and records any exceptions, and then publishes all this to a dashboard. Here's when the experiment first went live. You can see that around 2:20 a.m., they're doing a little over 2,000 merges. If you look very carefully at the bottom, you can see some tiny red tick marks, which is where merge and use and try disagreed for the merge. Here are bugs in their new code, but this hasn't affected their users at all because they're still getting the results of use. And so they fix and redeploy and fix and redeploy and fix and redeploy. They're also checking performance. So here's the performance graph, and the green code is the newer code and the blue is the old. They ran this experiment for 4 days until they had 24 hours with no mismatches and no slow cases, removed the old merge code, left the new merge code in place. At the end of that time period, they had done more than 10 million comparisons between use and try. So they had really high confidence that it was working exactly the way they thought it would. This is a great example of being aggressive about your engineering practices, like continuous deployment, but then building governance checks into that process to make sure you don't inadvertently break something. This is really about being able to adapt to incremental change in your architecture over time so that you can, in fact, adapt to things rather than constantly be in this lurching best practice to anti-pattern series. Recognize as things change and adapt to them as you go along. So I'll leave you with one last piece of advice here. And that is to be your own out-of-town consultant. So there is this phenomenon in the consulting world known as the out-of-town consultant effect. And what this says is that if you rode in an airplane to get to a meeting, you automatically have more credibility than the people who drove a car to that same meeting. And there's a correlation that the further you had to fly, the more credibility you have. This, of course, is not necessarily true, but there is some value to the out-of-town consultant effect. And it has to do with what turns out is this apocryphal story about boiling frogs that shows up in the Pragmatic Programmer book. So you're probably familiar with this story that apparently if you want to boil a frog, you can't just throw a frog in a pot of boiling water because they'll hop out. But if you put a frog in a pan of cold water and heat it up slowly, the frog will cook without realizing it. This story is apocryphal because it turns out that's not true. Frogs are not that stupid. But large organizations are. Teams constantly build these best practice things and until it starts doing active damage to their organization, and they don't notice because they're boiling frogs. The out-of-town consultant effect says that when you come in with an objective view, you can see those things and go, hey, that's really not the best thing you should do. And it gives you an objective insight into what's going on within that organization. So my encouragement to you is to be your own out-of-town consultant. Look at all of these practices and processes and things you're doing every day that you're in a habit of and ask, is that a best practice or has that become an anti-pattern? And should I really try to adapt that to make it a lot better? Thank you very much for having me. I hope you enjoyed it, and I hope you have a fantastic remainder of the conference.